We welcome you all. We are Department of Mechanical Engineering, Government College of Engineering, Bodi Nayakanur. We are going to present a topic on air conditioning system and load estimation, prepared by Professor M. Balamurugan, team head, and team members are Professor M. Sabha Karthik and Professor M. Vinod Kumar. So this is the syllabus of the 5th unit of refrigeration and air conditioning system. In this unit, we are going to study the design perspective of refrigeration system, going to calculate the cooling load for given confined space, and also study the human comfort and IAQ principles, effective temperature and shorts, and calculate the summer and winter air conditioning loads, and also study the air conditioning system with controls, pressure, temperature, humidity sensors, actuator and safety controls. Cooling load. So we are going to define the what is cooling load. The total heat required to be removed from the space in order to bring it at the desired temperature by the air conditioning and refrigeration equipment is known as cooling load. The purpose of a cooling load estimation is to determine the size of the air conditioning and the refrigeration equipment to give desired temperature or to maintain the desired temperature of the confined space. Next, the components of a cooling load. First one is the sensible heat. That means there is a direct addition of heat to the enclosed space. The reason here is the heat flow into the building by conduction through the exterior walls, floors, ceiling, door and windows, and heat absorbed by the wall and roof exposed to the solar radiation. The third one is the heat given by the lights, motor, machinery and cooking operations inside the confined space. The last one is the heat liberated by the occupants in the confined space. Latent heat gain. That means there is an addition of water vapor to the air of enclosed space. The reason here is the heat gained due to moisture in the outside air entering by the infiltration. The next one is the heat gained due to condensation of moisture from the occupants. The total load is equal to sensible load and latent load. Here, the first one is the sensible heat gain through building structure by conduction. It's like a normal convection problem. So consider a building wall composed of a single homogeneous material. A little consideration will show that heat passing through the wall is first received at the wall surface, that is exposed to the region of higher temperature by radiation and conduction. Then the heat flow through the material of the wall to the surface exposed at the region of lower temperature. Now the heat is transferred to the inner side of the wall to the space. The next, this is the simplest one. The next one is a building wall composed of composite wall. The thickness of wall is higher. It made up of different materials. It's also exposed to the high temperature on one side, lower temperature on other side. The heat transfers from the high temperature side to low temperature side through the conduction mode. So this is the example of composite wall. Composite wall made of three different materials. The material name is A, B, C. So T1 is the highest temperature, T4 is the lowest temperature. The heat transfer from left side to right side through the conduction mode. In some case, we consider the high temperature air and the low temperature air to calculate the amount of heat transferred to the space. Here Q equal to the amount of heat transferred through the wall. Q equal to U del T. So U means overall heat transfer coefficient, del T temperature difference. So 1 by U equal to resistance of the composite wall. This is the formula F naught, heat transfer coefficient of outer, Fy, heat transfer coefficient of the inner, and the conduction resistance. The heat gained from solar radiation, that means irradiation. The solar radiation striking the outside surface of a building may be contributed appreciably to the peak load on the refrigeration and air conditioning equipment. Therefore, we consider the solar irradiation strike on the outside wall of the confined space. This solar irradiation depends upon the following factor: altitude, angle of the sun. It also depends upon the altitude, angle of the sun, and the clearness of the sky, absorptivity of the surface of the wall, and portion of the surface exposed to the sun. The next one is the heat gain due to infiltration. The infiltration means infiltration is the air that enters a confined conditioned space through the window cracks and opening of the doors. There is the crack and opening in the windows and doors. Due to this opening, the air pressure difference, the air enter from outside to inside of the conditioned space. This is the reason is the pressure difference on two sides of the window and doors, and also it depends upon the wind velocity and its direction, and also difference in density due to the temperature difference between the inside and outside air. Next, the heat gain due to ventilation. So ventilation is provided to the conditioned space in order to minimize the odor, concentration of the smoke level, decrease the carbon dioxide level and other desirable and undesirable gases, so that freshness of the air could be maintained. The quantity of the air used for ventilation should be provided at least 1/2 of the air per hour in building with normal shielding heights. Next, the heat gain through the ducts. The heat gain due to supply duct depend upon the temperature of the air inside the duct and the temperature of the air surrounding the duct. We can calculate the heat gain through the duct by using the relation Q equal to UA TA minus TS. So use the overall heat transfer coefficient of the duct, AD surface area of the duct, TA ambient temperature of the air, TS temperature of the supply air inside the duct. Heat gain from lighting elements. It means there is in a conditioned space there is a lot of lightings and a fan. We fitted a fan and a motor and a cooking equipment. There is also release the heat. We are going to account that heat. Mathematically, the heat gained from the electrical light is given by Q equal to total wattage of lights and use factor and allowances factor. Next, the heat gained from the power equipments. So power equipments means like the fan, motor, other equipment of this type also add heat to the air in the conditioned space. The heat gain from the electrical motor is given by Q equal to power rating of the motor times load factor divided by the motor efficiency. The load factor is the fraction of the total load at which motor is working. Next, the heat gain from occupants. In a conditioned space, it is used to give human comfort. So the human body also release the heat continuously. In order to maintain the human comfort of the body, we continuously remove the heat from the conditioned space. So we are going to account the amount of heat released from the each occupant. So here the human body in a cooled space constitutes the cooling load of the sensible heat and latent heat. The heat gained from occupant is based on average number of people that are expected to be present in the conditioned space. Okay, thank you. So this is the cooling load calculation. We consider all the factors: amount of heat conduction through the wall, and in amount of heat added to infiltration, ventilation, lighting equipments, and other power equipments and occupants. These all the factors release the heat in the confined space. So the temperature of the conditioned space is increased continuously. We are going to maintain the desired temperature. We must remove all the temperature, all the heat from the conditioned space. So we are going to calculate the cooling load mathematically and select the suitable refrigeration and air conditioning system for the space to maintain the desired condition. Thank you. We welcome you all. Today we are going to see the problem in the topic of cooling load estimation. Here, the objective of the problem is to find the total cooling load in the conditioned space and decide the size of the air conditioning unit. In finding the cooling load calculation, we consider all the factors that we have discussed in the previous class and calculate the cooling load. In the problem, for the conditioning of a 4-meter high single-story office building located at 30° north latitude, the plan of which is shown in figure, the following data are given. This is the plan of the single-story office building. This is the outside walls. Outside wall, the size of the wall is length 27 meter, width 17 meter. This is the partition wall. This is door of the single-story office building, and these are the windows of the single-story office building. The given data are plaster on inside wall 1.5 centimeter and outside wall construction. That is the composite wall 20 centimeter concrete block, 10 centimeter brick veneer. Partition wall constructions are 30 centimeter brick. The roof construction 20 centimeter reinforced concrete cement slab with 4 centimeter asbestos cement board. The floor constructions are 20 centimeter concrete, and they gave the densities of the brick, concrete, plaster and asbestos board. The fenestration, they gave the fenestration size and the heat transfer coefficient at the windows U equal to 5.9 watt per meter square Kelvin, and they gave the door size, and the overall heat transfer coefficient of the air at the door is 0.63 watt per meter square Kelvin. Outdoor design condition is 43 degrees Celsius dry bulb temperature, 27 degrees Celsius wet bulb temperature. Indoor design condition is, that is the design temperature, 25 degrees Celsius dry bulb temperature, 50% of relative humidity. Daily range 31 degrees Celsius to 43 degrees Celsius. That means the variation of temperature on the outside of the single story office building, the temperature varies from 31 degrees Celsius to peak temperature 43 degrees Celsius. Occupancy 100. That means number of persons in the office 100%. Lights equal to 50,000 watts. That means the number of light that emit the power, the total watt of the power light is 50,000 watt. Assumed bypass factor of the cooling coil 0.15. Here the question is, find the room sensible and latent heat load and also the grand total heat load. Solution. They take the thermal conductivity of the glass and concrete, brick, plaster, asbestos from the table. They give the values and assumed film coefficients. Film coefficient of the air F0 23 watt per meter square Kelvin on outside air, inside air F5 7 watt per meter square Kelvin. Outside wall. Next, for the first step is we are going to find the overall heat transfer coefficient of the outside wall. We consider both the convective resistance of the outside air and inside air and the thermal resistance of the composite wall. Next, we are going to find the heat transfer coefficient at the partition. That value is 1.86 watt per meter square Kelvin, and heat transfer coefficient we have at the roof. The value is equal to 2.13 watt per meter square Kelvin, and finally we find the overall heat transfer coefficient of the air at the floor. At the floor, U value is 6.05 watt per meter square Kelvin. Then we find the area and volume of the office, single story office building. Then the ventilation rate for office. From the table, volumetric flow rate of the ventilation is 0.28 cubic meter per minute. Here, the total volume of ventilation air is 0.28 times 100. Per person, 0.28 cubic meter per minute. So total 100%. So volume of ventilation air is 28 cubic meter per minute. Next, we are going to find the mass of wall per unit area. So outside wall mass, we find the outside wall mass, that is 604 kg per meter square. Mass of partition wall 707 kg per meter square. Mass of the roof 401 kg per meter square. Then problem, they observe the solar radiation on the windows in watt per meter square unit. So they calculated they gave the data in the table, and we find the area of the doors, let's say door, and area of the windows. Outside wall area. The outside wall area, west side wall area 96 meters square, north side wall area, south side wall area. Partition wall areas of east side wall, north side wall. We calculate the areas of the outside wall areas, partition wall areas. They give the occupancy load, sensible heat load 75 watt per person, latent heat load 55 watt per person. And we assume the only 10% of the supply duct outside the conditioned space. The second assumption is no return duct outside the conditioned space. Then the third is the fan horsepower is 50% of the RS value. Next, we are going to see the calculation sheet for cooling load estimation. So this is the calculation sheet. First one, we find the space of the office, and the estimation time is 5 p.m. up to 5 p.m. The outside condition of the air 43 degree tribal temperature, wet bulb temperature 27 degrees Celsius, relative humidity value 29%. And the indoor desired conditions of 25 degrees Celsius dry bulb temperature, 18 degrees Celsius wet bulb temperature, 15 degrees Celsius, 50% of relative humidity value. The ventilation, next we give the volume of ventilation air 28 cubic meter per minute to 28 cubic meter per minute. Next, the sensible heat calculation. First, the solar irradiation, east side glass, there is no solar radiation. West side glass, the value is 5900 watt per meter square. North side glass 270 watt per meter square. South side glass 190 watt per meter square. Next, the solar transmission gain wall and roof. Next we going to consider the heat transfer through the walls and roof. So we calculate all the values in watts. Next, we find the heat transfer solar radiation through the doors and all glasses and partition walls. Next, we focus on internal heat gain. There are 100 people, so the sensible heat load 7,000 watt. The lights 1500 watt, so we calculate the sensible heat load value. So here we consider the factor, so 5% of the value. So supply duct, here we calculate the heat gain through the duct. So here in the problem 5% is 5% plus leakage value. Next he consider the effective room sensible heat, the infiltration value. The heat gain due to infiltration is 5940 watt, and the latent heat value, latent heat of the people 5500. The total value is 11,400 value. So the final this is the final effective room latent heat value 13,330 watt, and the total load is, the grand total is the summation of sensible heat load and latent heat load. The total load is 1 lakh, summation of sensible heat load and latent heat load. In this problem, the many designers don't take into the account of the infiltration load separately. They usually consider to be they usually consider the inflation in the, for example, in many designers don't take into account the infiltration load separately. It is considered to be taken care of by ventilation air. If the ventilation cubic meter per minute is greater than the inflation cubic meter per minute, on such simplified load estimation calculation sheet for the ground, first and third floors of a television studio building without considering the infiltration load. So this is the problem in the cooling load calculation. Thank you. We welcome you all. Today we are going to see the next topics in 5th unit of refrigeration and air conditioning system. We are going to study the air distribution system, filters, and the meaning of effective temperature. First, the air handling system. The air handling system consists of the air distribution system, the duct system, and the fan. The air distribution system comprising inlets and outlets. The various inlets for recirculated air, outlets for supply air. The next, duct system. The duct system including return duct, supply duct, and other apparatus like dampers, filters, coil, or air hose. The fan provides the necessary energy to move the air in the duct or air conditioning system. This is the schematic airflow diagram for an air conditioning system. This diagram shows how air is handled in a simple air conditioning system. A closed loop is formed for the circulation of air. In this case, the reference point is the room. It is at atmospheric pressure. The air enters the return duct through the inlet from the room. The pressure of the air decreases in the flow direction. and the air reaches the fan, the fan raises the pressure of the air. Then the air flow through the outlets to the room. So this is the simple airflow diagram of an air conditioning system. So the air from the room supplied to the return duct through the inlets, and the pressure of the air is decreases continuously in the flow direction, and the air pressurized by the fan, the high pressure air is flow to the room through the outlets. This is the simplest airflow diagram. Next, the requirement of good air distribution system. Here the requirement is the air distribution system should create a proper combination of temperature, humidity and air motion in the occupied zone or conditioned room with occupied zone, which is normally at 1.8 meter above the floor level. The next requirement is the variation in a temperature in a single room shouldn't be more than 1 degree Celsius. The temperature variation in the conditioned room should be less than 1 degree Celsius. The desirable air velocity is 9.1 meter per minute at the occupancy level. The principles of air distribution. The first one is the blow or throw. Blow or throw means it is the vertical distance travelled by the air in the horizontal direction on leaving the air outlet and reaching the velocity of 15 meter per minute. It is the distance travelled by the air stream in horizontal direction, simply in horizontal direction. Drop is the vertical distance the air moves after it leaves the outlet and reaches the end of the blow. Blow means horizontal distance, drop means vertical distance travelled by the air. Induction ratio or entrainment ratio. The air leaving the outlet is primary air. The supply air entrains some room called secondary air. So the sum of the primary and secondary is called total air. The induction ratio is the ratio of total air to the primary air. These are the blow, drop and induction ratio are the principles of air distribution system. Next, the filters. So filters use the principle of straining, impingement and interception. Filters filter the air. There are 3 grades of filters: roughing filter, pre-filter, high GPA filters in the refrigeration system. The roughing filter uses the principle of straining and it has number of layer of net with a layer provided with a resin, impregment, synthetic media. These all the layers are stretched together. Next, the pre-filters. The pre-filter use the method of impingement. It's largely depend on the inertia of force of the filtered particle. The third filter is the HEPA filter. These filters use the principle of combination of impingement and interception. This filter made of submicronic glass fibers. And aluminum separators are inserted between the submicronic glass fibers. These fibers are heat resistant. The strength of the fiber, the retaining is the strength up to 320 degrees Celsius. The filter pack is sealed into a aluminum frame using the suitable adhesive, also provided with a rubber gaskets on sealing the faces. The efficiency of the filter. The efficiency of the filter is the ratio of difference between the number of particles before filter and number of particles after filter to the number of particles before filter. Human comfort. The last topic is the human comfort. Human comfort is the condition of the mind. Condition of the mind which express satisfaction with the thermal environment. There are a number of factors affecting the human comfort. The first one is the effective temperature, and next heat production and regulation in human body. Third one is the heat and moisture losses from the human body. Fourth one, moisture content of the air in the conditioned room. Fifth, quality and quantity of supply air. Next is the motion of the air in the conditioned room. The first one is the effective temperature. The degree of warm or cold felt by the human body depends mainly on the following factors, or the human comfort depends mainly on the following factors: dry bulb temperature, relative humidity, air motion. Here the effective temperature combined the effect of these three factors, or in order to evaluate the combined effect of the three factors, the term effective temperature is employed. The numerical value of the effective temperature is made equal to the temperature of the still saturated air, which produces the same effect of or sensation of warmth or coolness as produced under the given conditions. So the effective temperature plays the major role in the human comfort, and the amount of heat released from the human body is the major factor. Our body continuously emit the heat in all the modes. Next, the heat and moisture losses in the human body. There is the sweating in the human body. The sweat, the liquid evaporate in the room. It increases the moisture content of the conditioned room. The fourth one is the moisture content of the air. The quality or the conditioned room should have minimum moisture content in the air. The next is the supply air from the refrigeration system should be high quality or pure air, and quantity, amount of volumetric flow of the air. The air motion. Next is the air motion. These are the factors affecting the human comfort. Thank you. Thank you. We welcome you all. Today we are going to see the topic of air conditioning control. This is the last topic of the 5th unit of refrigeration and air conditioning paper. We are going to study the control system. The control system is used to maintain the control variable. If there is no variation in the control variable, or there is no variation in the desired condition, we need not any controlling system. Suppose there is a variation in the controlling variable, we need some controlling system. The working of the controlling system is detect the variation in the controlled variable and measure the extent of variation and trigger the activating element and trigger the regulating element and minimize the variation. This is the working of the control system. Here we study the air conditioning control system. If the refrigeration load and capacity of a plant remain constant, there would be any need to have any control. That means there is no variation in the control variable. We don't need any control system. Suppose there is variation in the controlled variable, we need some control system. For example, there is a fluctuation in the refrigeration load and capacity of the plant. The load changes due to input condition change and output condition changes. The plant capacity also changes due to the changes in the outside condition. If there is a variation in the load and capacity of the plant, we need some control devices and change the controlled variable. Nowadays, we use the automatic control devices. The automatic control devices achieves a high degree of accuracy in maintaining the required temperature, pressure and humidities. In every control device, there is a controlled variable. In refrigeration unit, the controlled variables are temperature, pressure, humidity and flow control devices. Here the detecting element detect the deviation from the desired value of the controlled condition. And the next, the measuring element of the control unit measure the extent of this deviation and trigger the actuating element. Next, the positioner. The positioner is responsible for setting the value of the controlled variable. In case the force from the measuring element is not strong enough to activate the regulating unit, we use some servo motor and a relay to position the valve. The transmitting element also used in the control system. It is the one of the part of the control unit. This is the black diagram. This is the black diagram of the control unit. The detecting element detect the variation in the controlled variable. The measuring element measure the extent of variation in the controlled variable and trigger the activating element. Activating element gives the signal to the transmitting element. This transmitting element activates the regulating element and minimize the changes in the controlled variables. The common item of control involved here are given below. Expansion devices, automatic expansion valve, thermostatic expansion valve. Cutoff for refrigeration units, high pressure cutoff, low pressure cutoff. That is the back pressure valves. Liquid level regulating devices, high side float valve, low side float valve. Flow regulating devices, solenoid valves, check valves, water and brine valves. Thermostats, evaporator thermostat, room thermostat. Then humidity controls and motor controls. The common type of detecting elements are bimetallic, temperature sensitive electrical resistance, electromagnetic and humidity sensitive. Bimetallic elements. A bimetallic element comprises of two strips of dissimilar material with different coefficient of thermal expansion. These different materials are joined together and fixed at one end. If there is any variation in the temperature, there is the result in expansion of the bimetallic strip. We can increase the sensitivity of the bimetallic strip by increasing the length of the bimetallic strip. Two commonly used pair materials are brass and invar. Electrical resisting elements. The electrical resistance of the element changes with the temperature, whereas the copper has a positive temperature coefficient and constant and is independent of temperature, and semiconductor has a negative coefficient of expansion. Semiconductors are well suited in automatic control because of the numerical high temperature dependence. This is the Wheatstone bridge for electrical resisting elements. Electromagnetic elements. This is the black diagram of electromagnetic element. The magnetic field in solenoid. The magnetic field in solenoid is influenced by armature, iron core armature. The moving of the armature up and down, a change in current will occur. The moving of the armature up and down, there is a change in current will occur by means of amplifier. This change can made strong enough to activate the control devices. Again, the magnetic field in solenoid can be influenced by ion armature in a coil. By moving the armature up and down, activated by a sensing element, a change in current will occur. By means of amplifier, the changes can be made strong enough to activate a control devices. Humidity sensitive elements. The two temperature sensitive elements used to measure the dry bulb temperature and well bulb temperature. Hence, we measure the humidity. The two thermistors also be similarly used coupled into a Wheatstone bridge. Such a device will operate on the basis of increase or decrease in the temperature difference, dry bulb and well bulb temperature of the air for the control of humidity. So we measure the two temperature and find the humidity value. This is the black diagram of the humidity sensitive elements. Thank you.